you should know that if you go a particular distance away and have a second charge Q2, you've got your main charge Q1. What's the force between those two charges at a particular radius? This is what we kicked off with you a couple of weeks ago. Oh. Okay. So the force depends on Q1, Q2 over r squared, 1 over 4 pi epsilon naught. That's the Coulomb force. At any particular point, you have an electric field vector E, which is 1 over 4 pi epsilon naught Q1 over r squared, because that's the field divided by the charge that you place there to determine whether there is a field there or not. So you've got those two equations so far. There is a third one. For at any particular point here, there exists not only the field, which gives you the force, but because if you put a second charge there, it's capable of doing something. It's got an ability to either move, it's got an ability to move something else, so it must have what? It can move things, yep, so it's got an ability to accelerate. So what must it have to actually be able to do these kind of things? Just in the same way, if you've got to give a car something to give it acceleration, what have you got to put into the car to get it? It's got to have energy. So we've got to have, at any particular point here, there must be some potential which can then translate into potential energy. So at any particular point here, r away, the potential at a point has an equation. And the equation for potential is slightly different. It's still that same constant, 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. It certainly depends on the charge that you've got there, Q1, and then you divide it by the distance you are. So for potential, it's just 1 over 4 pi epsilon naught Q1 over r. It's not r squared. To give a full explanation for why it's r, not r squared, you'd actually need to do a fair bit of integral calculus to integrate from the force through to get the energy, and by doing the integration, you would end up, that squared would become just r. More equation, because if we put a second charge here, Q2, in this case down here, at that point where there exists an electrical potential, what will that charge therefore have? And I think you mentioned it before, Chris. There's potential there at a point without putting a charge there. As soon as you have a second charge, say a positive charge Q2, what's stored there because of the fact that you've brought that second charge close to the first one? There must be energy stored there because you've had to physically bring that charge and push it towards that one at that point there. The further you push it in towards it, the more energy must be stored because you're pushing it closer and closer together. So if you're pushing energy into something, there is energy there. And in that case, the energy that's stored, what equation is going to give you the electrostatic energy for that second charge being at that place, r away? Yeah, because you've got the definition of potential is the work done per unit charge. So it's the work done in bringing that charge divided by the test charge that you've used there. So in this case, W is 1 over 4 pi epsilon naught Q1, Q2 over R. Does this sound similar to anything else that you've done over the year? Gravitational potential energy. It's a very similar thing that we've got here. With gravitational potential energy, the energy was always negative because you're always dealing with two things that are attractive. Here, if you've got a positive and a negative charge, you'll end up with negative energy. But here you've got positive and positive charges, so you'll end up with positive energy. You've had to push the things together. Again, with gravitational potential energy, it's just divided by R, not R squared. The units there would be joules for potential energy. The units here are going to be volts, provided that you're using coulombs and meters and the appropriate units for the constant in the equation there. So really bringing a lot of the electrostatics here, making it quite similar to what you've done with gravitational, so almost revising what you did with gravitational potential.